Yeah, the live streaming is working now.
You need to allow the participants.
Yeah, now how do I, Bibila ma'am?
Yeah, she's ready.
Yeah, we can start now.
The participants all?
Yes, yes.
Yeah. Good morning all. I'm happy to introduce next session speaker,
Dr. Vedran Jovic. Today he'll be delivering his talk on the topic direct nodal lines and flat band surface state in the functional oxide RuO2. Dr. Vedran Jovic is currently the research and development scientist in GNS Science, New Zealand. His work involves the development of materials and processes for electrocatalytic hydrogen production and conversion of C1 molecules to higher value chemicals. His postdoctoral work was at the Advanced Light Source Synchrotron of the Lawrence Berkeley National Laboratory in California from 2014 to 2019. He had completed his PhD at the University of Auckland from 2010 to 2014. Furthermore, he is experienced with an extensive range of characterization techniques, specifically applied to the fields of material science and chemistry and broader disciplines. He has published more than 26 publications in international journals. Now I invite Dr. Vedran Jovic to deliver his talk.
Thank you very much for the kind introduction. So I will I will now share my screen with everybody.
Yeah, yes.
No, you can share your screen.
Sure. Okay. And everybody I guess sees this?
Yes, yes.
Okay. Okay. Well, thank you once again for inviting me. It's really a pleasure to give this presentation. So I'll get right to it. Today I will talk to you about our work on ruthenium dioxide and discovery of these direct nodal lines in this flat band surface state, and it's very highly functional oxide. So as I said in the introduction, I completed this work at the Advanced Light Source Synchrotron, which is a facility in Berkeley, California. So it's just in the San Francisco Bay Area on the hills and the Berkeley town of Berkeley, looking over the bay there. You can see. So it was done. This work was done around 2018. We spent a lot of time collecting this data, many sleepless nights, and we managed to compile a nice little story, which I will share with you today. So before I get into it, I'll just give you an outline of today's presentation. So let me just start by highlighting some of our findings on our angle resolve photo emission work on this material. So our results appear to be some of the first reports on bulk direct physics in a functional oxide. So in particular, this ruthenium dioxide, a material with really concrete applications. So by means of this state-of-the-art angle resolve photo emission spectroscopy, we'll observe a network of what's called direct nodal lines in the Fermi surface of this industrial catalyst. And some of these findings you'll see even contradict some recent theoretical predictions. So this direct nodal line gives rise to what's called a flat band surface state. This is the so far unobserved analog of the drumhead surface state predicted for nodal ring semimetals. This phase also opens the gateway for the study of exotic phenomena like unconventional surface superconductivity or long-range Coulomb interactions. So, and our results for the first time try to establish or attempt to establish a link between the fundamental topological properties and the surface functionality of a energy relevant material. And you'll see that these direct nodal lines actually what they do is they host these nested hotspots in the Fermi surface, which are actually postulated to be related to the magnetism in this material. So in the first part, I will show you the Maestro beamline, where we perform the work, and I will provide the insight into some of the physical nature of the single crystals that we worked on. And then next, I will take a look at some of the concrete applications of ruthenium dioxide, and will identify the chemical and physical properties behind its functionality. In particular, we will also take a deeper look at the crystal structure of ruthenium dioxide and look at the non-symmorphic symmetry in the material and its influence on the formation of these direct nodal lines. In part two, we'll also take a look at the ab initio calculations based on the DFT and what they say about the direct nodal lines in the band structure of the metallic ruthenium dioxide. And in part 3, I will show you this scenario, that the scenario defined by theory is actually confirmed by these RPES measurements at the 110 surface of the material. And this actually presents one of the first observations of relativistic direct fermions in a functional oxide. We'll do this by first looking at DNLs of types A and type B. And then even more fascinatingly, we will see in part 4 that we find striking evidence of a third type of direct nodal line along the XR direction of the Brillouin zone, which produces a continuous direct crossing at the Fermi level. We will see that this direct nodal line serves as an anchor line for this non-dispersive flat band surface state, what seems to be the analog of this theoretically predicted but experimentally elusive topological drumhead surface state. And in part 5, we will take a look at the robustness of this flat band surface state by depositing potassium on the material and monitoring the RPES response during deposition. So we'll see that it has a very sensitive response to of this state to doping, and a strong loss of coherence in response to the changes in the electrostatic environment within the material with doping. Okay, so let's start by setting the stage for our main results. So we'll take a look at some of the background, and to see what we are working with and how we prepared the material for measurements and also the measurements that we performed. So these iridium doped single crystals were grown by chemical vapor deposition at the growth facility in EPFL in Lausanne by the group of actually Helmut Berger. They followed the recipe described a long time ago by the work of Schaefer. And if you follow it carefully, like our colleagues did, you'll see that in about 2 weeks' time, you're going to grow single crystals. And our XPS core level spectra showed that at several different energies verified that we essentially have a doping level of 7% iridium in this material. And then X-ray diffraction confirmed that we indeed have this rutile crystal structure with its respective crystal parameters. So it's consistent with ruthenium dioxide. And there's a little schematic of the crystal structure. We performed the spectroscopic measurements on the single crystals at this Maestro. Hello? We performed the measurements at this Maestro beamline of the ALS. And this is a remarkably sophisticated beamline in terms of infrastructure. It has multiple UHV growth chambers, a PEAM and LEAM system, and a nano RPES and a micro RPES chamber. And they're all fully interconnected with each other by this thing that they call the Maestro Area Rapid Transport System, which if you've been to the Bay Area, you know, is analogous, or it's a little tie into the Bay Area Rapid Transport System, which is called BART, their subway system. So this UHV highway essentially allows you to move the materials all around the chambers, all by not exposing the perfectly crystalline surfaces to any atmosphere. And this is and because these are highly surface sensitive techniques that I'll be showing you, this is highly important. And we performed our measurements in the micro RPS chamber, which is circled, or a square is put around it. To get these ruthenium dioxide crystals ready for measurement, we placed in a series of crystals on copper pucks, and then we essentially cleave them in the chamber. And these chambers are at 5 by 10 to the -11 torr. And these single crystals have reproducibly small 50 micrometer clean facets of the thermodynamically favored 110 surface. And we confirmed this by Laue diffraction. And actually the synchrotron beam spot size is on the order of something of around in this measurement, perhaps 50 to 20 microns or less, so well below the facet size of these domains that we're looking at. The data was collected in the with p-polarized light with the polarization vector, as well as the entrance slit to this spectrometer in this horizontal scattering plane. So the 110 crystal axis was then further oriented along the analyzer slit with the 1bar10 surface vector pointing towards the analyzer, as I've shown you in this schematic. Okay. So now let's take a look at some of the current and potential future applications of this material so that we can understand some of the motivation behind the work, and also we can start to relate the material's applicable properties to its solid state physical properties. We'll also take a deeper look at the non-symmorphic symmetry in this sample and its influence on the formation of these direct nodal lines. We'll do this mainly through the lens of ab initio calculations based on the density functional theory. And this section will really set the stage for our experimental results, which we will then present in section 3. So ruthenium dioxide in many senses falls in line with other binary 4D transition metal oxides. It's a good metal. And it's believed to be a polyparamagnet. But from the point of view of correlated electron physics and magnetism, it's really seems to be one of the least interesting 4D transition metal oxides. However, in terms of functionality, it's one of the most functional materials, and it owes its functionality to its electronic and ionic conduction properties and favorable thermal and chemical stability. It's very in some instances, corrosion resistant, and its diffusion properties are beneficial for various sensing applications. However, it has also particularly high Coulombic efficiencies, its ability to facilitate an electrochemical reaction, and it has very good mass transport properties. So this material is actually a prototype conversion material on metal oxide, lithium-ion batteries, electrodes, high charge storage capacity, supercapacitors, and all of these kinds of neat applications. But many of these favorable chemical and physical properties are responsible for its high efficiency as an electrocatalytic material. The most industrial process is called the VCAN process, where it serves as a catalyst to energy efficiently recycle hydrochloric acid, thereby replacing very energy-intense methods based on electrolysis. In catalysis, it's also known to serve in many oxidation processes. It's even being looked at for dehydrogenation of various small molecules. So now that we've outlined some of this functionality, it's actually the functionality of this material is believed to stem from its complex electronic and magnetic properties. And this is determined by a combination of lattice spin rotational and time reversal symmetries, as well as this balance between the Coulomb and kinetic energies in this transition metal oxide. Because of this, the electronic structure of ruthenium dioxide has gained heavy experimental and theoretical interest. And now there are hints that the functional catalytic properties can be related to specific niceties of the Fermi surface. For instance, first principle calculations actually believe that these magnetic moments are responsible for many of these catalytic applications. And such magnetic moments are actually confirmed by neutron scattering, and they have been attributed to the spin density wave instability driven by particularly large density of states at nested hotspots in the Fermi surface, which I will show you. And these in turn are believed to be a direct consequence of the non-symmorphic symmetry of the material, of its crystal structure. And this establishes then an intimate link between the fundamental properties of the material and its surface functionality. Okay. So let's take a look at the significance of this non-symmorphic symmetry in ruthenium dioxide, which was recently discussed in the framework of topology and relativistic physics in a very nice theoretical paper by Jan Sun. So if you look at this paper, it essentially tells an experimentalist who wants to measure the band structure of the material. What does it tell an experimentalist? It tells us that the symmetry considerations in conjunction with theory predict a network of these so-called Dirac nodal lines close to the Fermi level. And in contrast to the more prominent Dirac and Weyl semimetals, which have host fourfold and twofold degenerate zero-dimensional Fermi points, Dirac nodal line systems have a one-dimensional Fermi surface. It's just this symmetry-predicted crossing of the conduction and valence band along a discrete line in K-space, and it has relativistic fermions close to this crossing point. And they're typically protected by crystalline symmetries. And in particular, they emerge in systems which have inversion symmetry, non-symmorphic symmetries, or time reversal and mirror reflection symmetries. And this forces and this protected crossing of the conduction and valence band along certain trajectories in K-space. Sorry. And there are two direct nodal lines in ruthenium dioxide, which I will denote here, type A and type B. And if you look at type A, first, time reversal and inversion symmetry in unison with a mirror symmetry protect this band crossing along the 110 and along the 110 planes. And this produces a network of fourfold degenerate and 2 spin and 2 orbital topologically non-trivial direct nodal lines. The second type, and then here I outlined them on the Brillouin zone. The second type, and actually this is a simulation of direct nodal line 1. And then the second type of direct nodal line is the topologically trivial one. It's protected by non-symmorphic glide mirror symmetry. In brief, this is the ruthenium dioxide lattice is a bipartite composition of 2 sublattices with different ruthenium oxide O6 octahedral orientation that are related by a fractional lattice translation of about half a body length, reflected by about the 110 plane. So in an analogy with the diatomic system or diatomic chain model, this glide plane effectively doubles the unit cell and backfolds the electronic bands. In conjunction, and then in conjunction with time reversal symmetry, it produces these 2 spin and 2 orbital, so degenerate direct nodal lines along the KX boundaries of this primitive Brillouin zone. And if you have spin orbit coupling in the system, it'll essentially direct nodal line 1 will gap, resulting in the anti-crossing of the 3D manifold, which is expected to produce a large intrinsic spin hole conductivities, similar as in iridium oxide. And this will also partially gap the direct nodal lines 2 along the Brillouin zone boundary, but additional symmetries will protect the fourfold degeneracy along discrete high symmetry lines in XM and MA, along the XM and MA directions of the Brillouin zone. And then the intersections of these direct nodal lines, they produce 6- and 8-fold degenerate points, specifying them as hexatrupel and octatrupel points in the Brillouin zone structure. So we move on to the next stage. And so in this section, we'll just take a look at the scenario and using RPES on the 110 surface of this slightly N-type dope iridium ruthenium dioxide. And we'll present a rare observation of the relativistic direct fermions in a functional oxide. So to identify the high symmetry planes within the complex 3D band structure, we employed photon energy dependent RPES. So this is the experimental surface along the 001 plane, compiled from RPES measurements in the range of 60 to 800 EV. And then you have the projection of the 3D Brillouin zone is marked in black, and the non-primitive Brillouin zone is marked in red. So there you go. This is based on the model that I showed you earlier. And then the circular contours, actually, you'll see that they're enhanced in every other Brillouin zone. It means they're following the RU sublattice rather than the primitive periodicity. And this is a hallmark of the non-symmorphic glide mirror plane of ruthenium dioxide. And then from this periodicity, we can identify cuts along the 3D Brillouin zone close to the high symmetry planes, which I've shown you in the plot. And at this energy, we acquire the Fermi surfaces and our data sets. So the analyzer is actually equipped with these deflectors, which allow you to maintain the sample in one position without actually moving, so that sample remains fixed instead of moving it to collect the Fermi surface. So you're actually not drifting away from the spot that you're measuring, which is very important if you're measuring samples of such a small dimension. And then as illustrated in the top panels, you can see that the RPES, so we have 3 Fermi surfaces, one at 69, and the cuts close to the 110 plane that contains both the X and R high symmetry points. And then you have 2 Fermi surfaces at 87 and 131 EV photon energies, which probe the Brillouin zone close to the 110 plane, but at slightly different points in the Brillouin zone. And I will show you evidence for this in the upcoming slides. Okay. So just to confirm the theoretical scenario predicted on the previous slide, let us first focus on the Fermi surface collected at 131 EV. And as I showed you, the photo emission hemisphere close at this energy cuts close to the Brillouin zone along the GMAZ plane of the of the Brillouin zone, and then with the direct lattice parameters of what we found from our XRD. We can then sketch out the primitive Brillouin zone in black, and we identify 4 main contributions to the Fermi surface, which are represented in this little schematic. First and most importantly, we observe these convex structures halfway between G and M. These represent one branch of the direct crossing that forms the unexpected third direct nodal line, and I'll show you this later. Second, we find intense spectral features labeled O and P along MA. These are the intersections of direct nodal line 1 and 2 in the XR momentum plane. And they are complemented by weaker features HP along the gamma Z direction, where the direct nodal line 1s cross each other. Third, we find these fuzzy horizontal streaks connecting the OP and HP points, which represent the spin orbit split residuals of direct nodal line 1. And as we will see later, these are actually what hosts the connected hot streaks claimed to be responsible for magnetic instability in this material. And fourth, and fourth, we'll identify 2 prominent arcs spanning between the features 1, and this is the signature of the flat band surface state. So the ARPAS band structure along the high symmetry path is well reproduced by the density functional theory. And following this discussion of Jan Soon in his paper that I referenced earlier, we directly identify the intense and band feature along MA, the direct nodal line 2. Surprisingly, we actually find remnants of a hexatriple point about 0.13 eV below the Fermi level, so 0.79 below the prediction of DFT. And this is actually a bulk DFT description, which misses the non-dispersive flat band surface state along the gamma M line as well. And then we take a look at the expanded view of the DNL2 along MA. It highlights the band maximum at the OP point. If we take perpendicular cuts, and this is the OP point that I mentioned in the Brillouin zone, and if we take perpendicular cuts at the prominent momenta shown by the white lines in the top figure G, and we plot them here as H1 through to H5, and there you go, H1, and they reveal for us the appearance and evolution of the direct crossing at OP and A. And then the curvature of the displayed in the panels exemplifies this crossing and shows excellent agreement with the DFT predictions in the earlier plot that I showed you. Okay, so, yes, okay, let me just move on a little now. I won't, in the interest of saving a bit of time, I will move on to the next part. Okay. So as I briefly mentioned in the outlining slides, surprises really came to us when we inspected the Fermi surface in the 110 plane containing the X and R high symmetry points of the Brillouin zone. Here we found a third nominally gapped direct nodal line that escapes the predictive power of density functional theory, and it remains surprisingly robust despite strong spin orbit coupling. And actually identifying this line was a huge mission. And when we first started to study this material, there was really no ARPAS studies out there on it. So we did a complete overview of the material's band structure. And this was somewhat evidenced from the very large 30 to 800 eV photon energy scan. And it was able to identify the following direct nodal line, which was by literally doing Fermi surface maps every 5 E steps and slowly analyzing each map for changes in the Fermi surface. So then panel A shows the Fermi surface at 69, and it probes the Brillouin zone along the 110 plane close to the XR line, high symmetry points. And once again, we have a little schematic. See what's going on. We see 4 features once again. We see the double arcs centered at the X points. These represent the 2 branches of the direct crossing that forms the direct nodal line. And they extend to the towards the zone and center to form this faint onion dome. The observation of this direct nodal line is restricted to a very narrow energy window around 69 eV. And this is shown in the momentum dispersion curve here that you see, where the ARPAS hemisphere probes closest to the XR line. And then you can see both branches of this direct nodal line. And then next we find the intense spectral features labeled DP. These are the intersection points of direct nodal line 1 with the XR momentum plane. So as you can see in that little schematic. And then third, we find the hot streaks, which mark the projections of DNL1 onto the XR plane, and their intersection with the XR Brillouin zone boundary marks these hotspot features in the Fermi surface, which I've actually labeled on top left, and they claim to be responsible for this magnetic instability. And lastly, we find the prominent arcs spanning in between these agents in direct nodal line 3, and they're the signatures of the flat band surface state. And now we dwell a little bit more into each of these features that we saw on the previous slide. So first we focus on the direct nodal line 3, and we can do this by taking a horizontal band structure cuts for 5 select momenta along the label D1 through 5 corresponding to the cuts that you see on the bottom left. And these plots reveal the evolution of the direct nodal line crossing spanning the line from X towards R. So, and then the DFT calculations actually reproduce this direct crossing astonishingly well, but located 0.5 eV above the experimental value, which is a striking deficit of the oversimplification of the DFT approach. And then third, the corresponding 3D band structure model in figure 1b, it correctly reproduces the continuous fourfold band crossing of the direct nodal line. And the degeneracy is supposed to be lifted by spin-orbit coupling, but as it is strictly symmetry protected along the XM line, this spin-orbit induced splitting effect is essentially very weak. And it actually does remain unresolved by ARPES. It's not easily picked up. And then you have the features labeled DP in the schematic, and they represent the intersection points of direct nodal line 1 with the 110 momentum plane. And both the ARPES and DFT, they reproduce this well. But again, the gap remains unresolved. And finally, we take some brief cuts along the other direction, along 110 at representative momenta. And we next to this onion dome, and we observe this continuous evolution of the direct states at the direct point towards a band with a hole-like parabolic band maximum at the hotspots, at these hotspot features. And this was correctly predicted by DFT. This evolution is very smooth for the intense hot streaks in the Fermi surface, and the projection of the first direct nodal line onto the it's smooth with the projection of the direct nodal line onto the XR momentum plane. The nesting of these parallel hot streaks along these vectors, as well as their simultaneous electron and hole-like character, and favors potential Fermi surface instability, such as spin or charge density waves. And in addition, the intersection of these streaks along the XR boundary lines along these hotspots are symmetry protected by this non-symmorphic glide plane of ruthenium dioxide. And then lastly, let's just, let's just skip this part and move straight to the, taking a look at the, how the state behaves, the flat band surface state responds to dosing of potassium. And then we'll monitor the ARPES signal and response. So the spanning of this flat band surface state between these adjacent direct nodal lines, as well as its unchanging energy dispersion, suggests that the state represents the so far elusive analog of this drumhead surface state. And to test its robustness, we deposit potassium, and we take a look at the overview of the results. And panels A and B show the continuous doping evolution of the state at various points in the Brillouin zone. And then with increasing doping, the flat band surface state just collapses and disperses to a lower energy. The states associated with the direct nodal lines populate only slightly, and they producing this Fermi surface bifurcation in the momentum dispersion curve, as you can see here. And then in panel D shows the core level evolution before and after potassium doping. So with respect to before doping, the post-deposition Fermi surface reveals over a broader and fuzzier spectral weight. But even though the bulk derived contributions related to the third direct nodal lines and the hotspots remain intact, the flat band surface state disperses and then washes away. And let me just skip a little bit forward because I'm cutting into everybody's time. And then so this essentially the sensitive response of this flat band surface state to, let me just skip a little bit for time and summarize the slide. The sensitive response of the state to this doping essentially indicates a significant loss of coherence in response to this changes in the electrostatic environment. While the potassium-induced surface disorder plays only a minor role, this effect is a result from this augmented scattering of the state with quasi-particles from the metallic bulk of ruthenium dioxide. Such scattering is really enhanced in these Van Hove singularities, which enhance the Coulomb interactions and the correlation of the surface electrons. So even in the presence of relatively weak perturbations, we may expect very exotic symmetry broken states to arise in this material, such as surface magnetism, surface superconductivity, or even like these graphene-like Landau levels. But and unfortunately, these kind of studies we didn't get to, and we'll have to leave them for future work. Okay, and then the whole presentation was, this is just a summary slide of everything that I've said. You can take a look, I won't go through it again. I believe I'm just on my time limit, so I will conclude there. Thank you.
Thank you, Dr. Jovic. We have some questions from the participants.
Sure.
Dr. Jovic, can you hear me?
I can hear you. Yeah.
Yeah, we have few questions from the audience.
Okay.
The first question has been raised by Ms. Danya. Can ruthenium oxide be used as hydrogen storage material?
That is an interesting question. The hydrogen storage materials are, I mean, if you could frame it in such a way that it has a very high surface area, I would imagine so. We would have to take a look at the essentially the absorption and desorption energies of hydrogen onto the surface in a possibly if it dissociates onto various sites on the in the framework. It depends on if you were to, I mean, I've never looked at it for the surface, but if you were to look at it, you'd have to start essentially with a bare surface, a stoichiometric surface, and then take a look at the adsorption energies, I suppose, adsorption, desorption. It's a good question. I haven't looked at it for this purpose. I can't answer directly, but it, yeah, would take some investigation.
Yeah. Okay, thank you. Our next question, Ms. Jayabharati wants to know about the stability of the material.
That's also an interesting question. In some instances, a lot of you may know that it's a good electrocatalyst as well for various processes, and it depends a lot on the potential which you apply. Is it an anodic potential or a cathodic potential, and the conditions that the reaction is run under, if it's in base or an acid. In some instances, it certainly will corrode. It will oxidize to another phase of ruthenium dioxide. It could, not even ruthenium dioxide, may form RuO4. So yes, it will corrode, but there are ways of stabilizing it depending on which application you are looking at. It's not the most stable material, but there is certainly ways of stabilizing it.
Okay, thank you. Next, another question by Mr. Anuj Kumar. Since ruthenium oxide is expensive, what are the other materials which can be used to replace it?
That's that is a good question. If you look at the theoretical papers by Jan Sun, you will be able to predict elemental compositions that may have similar properties to ruthenium dioxide. Although, if you consider ruthenium dioxide amongst the other noble metals and precious metals, it is actually substantially less expensive than some of them. Many, up to 40 times less expensive per certain unit weight. But I would suggest in this case to look at the similarities in the crystal structure and what they can tell us, and then how that impacts the electronic structure, and then maybe some analogous materials could be predicted. But it's these certain group of metals and their oxides are highly functional, and a lot of the functionality is related to what I've been talking about here. So if by dwelling deeper into these crystal structures and electronic structures, I'm certain that analogous materials could potentially be predicted.
Okay. Thank you, Dr. Jovic, for your interesting lecture. And also thank you for accepting our invitation.
Thank you very much for inviting me. It's a really pleasure.
Yeah. Thank you, Dr. Vedran, for the interesting talk. Thank
Thanks
you very
a
much.
lot.
Yeah. We'll meet again. Yeah.
Yeah. Thank you. Bye. Bye.
Bye. Have a great day.